Hi, everyone, and welcome. We do have a few more people who are jumping on the call right now, so we're going to wait a few minutes before we get started, but we are going to have a great presentation from one of our engineering managers, Chris Koska, on design for performance versus design for manufacturability. So we'll give it just a few more minutes, and then we'll get started. For everyone who just jumped on the call, we are just giving a few more minutes to let everyone log on and get settled, and then we'll get started with today's presentation. All right, I know we still have a few people joining, but let's go ahead and get started. So to everyone on the phone, hello, and thank you for joining us. I'm Julie Anna, a marketing specialist from MW Industries. Today's presentation is Design for Performance versus Design for Manufacturability. During the presentation, we'll be discussing performance and manufacturability principles for valve springs specifically. Our presenter today is Chris Koska. Chris is the plant and engineering manager at Mohawk Spring, an MW Industries company. He has 17 years of experience in spring design for valve applications, including how to optimize performance and increase manufacturability. Supporting the webinar and questions today will be Chris Leo, also from Mohawk Spring. We have left plenty of time for a Q&A session at the end of the call today, so if you have questions during the webinar, please type them into the chat or Q&A module at any time. We will hold those questions until the end of the call, but we'll make a note of them and ask them later. So feel free to ask them at any time. For those interested, this webinar is also being recorded and will be available for review later. Now, I'll pass it over to Chris to get started with the presentation.
Thank you, Julie. Hello, everybody. Good morning, good afternoon, depending on where you're at. My name is Chris Koska. I am the plant manager of Mohawk Spring, a division of MW Industries, and also an engineering manager. As Julie stated, I have 17 years in the spring industry, including valve applications. I've spent probably a good sum of that 17 years dealing with the customers on their valve applications and helping them in design. I've released multiple case studies to the spring industry on valves and valve applications and the do's and don'ts. I am on the board of directors for the Midwest Spring Association, which is called CASME. Been a member there for about 3 years. I've released some white papers on spring toleranting, including squareness under load applications, which you could find in the Valve World magazine. So let's go ahead and get on with our presentation here. So as you know, the springs are the most critical component of any valve application. And when we talk about valves, we're going to be talking about static applications. We're not going to be talking about cyclic, multiple dynamic applications, which are multiple of cycles on a spring. We're going to kind of cover performance of the spring and how that works with the valve, mainly on how the valve seats. We're going to talk about costs, and we're going to talk about offering best quality at an economical price, and we're going to talk about how to bring better speed to market, which is basically when a customer's designing a new spring, what do's and don'ts could we avoid and do to actually help you get that product out to the market quickly. So we're going to only cover one type of one type of valve application here. I'll use some examples, and it's going to be a safety relief valve. So when we go on this presentation and you see some pictures of some springs, they will be mainly relief valves. As you know, valves, again, they're static applications. They're critical to air and gas flow applications. Um, and they come, there's various different size valves, as we all know. The springs can be very small and can be very large. So when we talk about design for performance, what we're going to be covering here is we're going to cover kind of what constraints customers can see when they are going to a supplier late in a design stage. And mainly what you're going to see, what we see, excuse me, is we see a lot of existing assemblies, so drawings we get from a customer, and they've already got tolerances on it. They've already spent probably 6 months to a year and finally come and give us the drawing and say, okay, this is what we need you to make. And what we see is a lot of restricted envelopes, which means we find that the customer's not really leaving us a lot of tolerancing room on the fit and function. As you know, springs don't fall under machine tolerances. We follow our own tolerances, which are spring industry tolerances. And a lot of times when we help them design late in this process, we have to deal with high cost materials, or we're looking at wire sizes that are difficult to get, which are probably not stock sizes. We're helping them with the springs that are difficult to manufacture. So we'll cover what we mean by what's difficult to manufacture. But that could be something that, say, a spring index, which I'll cover later, is too small or too large, or we're developing stresses that are way above what we would want to design for them. So when designing springs, we are finding that a lot of times we have a lot of delays. And those delays occur because we're doing multiple sample runs for the customer. And that's because, again, as we stated, we're designing to tolerances that are tighter than what we'd like to see. So we're trying to give them that tightest tolerance for them to fit in their assembly, and they find out that it's not working, so they have to go back to us. We're designing with expensive materials. So an example is maybe there was an opportunity of using a good quality wire and have, say, it being plated, but that doesn't fit in the application, and we have to use some other stainless steel or exotic alloy, which I'll cover later in this webinar, that again may give you lower stresses, but are going to affect the performance of the part in other ways. And also we see that we have to do a lot of secondary operations, which I'll cover in the webinar. If we are able to help with the design, or your spring supplier could help you early in the design, we could avoid any kind of secondary operations to achieve certain stress levels, which we'll discuss later in this webinar. So an optimal spring design process. So when we talk about an optimal spring design process, what we want is we want to use the best practice tools in the design stage. So what are best practice tools? So some of those tools are using spring industry tolerancing. So we want to definitely adhere to the spring industry tolerances, and we're gonna emphasize that a lot in here, because again, it comes back to the customer to understand that spring industry tolerances are different than machine tolerances. It's very important to use those tolerances because it makes it easier to manufacture the part. We want to design at the lowest stresses possible. So if we come in early enough, when a spring supplier comes in early enough to help you, they're going to give you the best design with the application and design it to the lowest stress possible. And we're also going to look at other manufacturing principles. For instance, a lot of times that things that get missed in the design process is the shape of the part. If it's going to nest in the application, say the part is designed with such a big pitch, that a lot of times you're not going to catch that this thing's going to tangle and it's going to create disruptions in your assembly, because your assemblers are going to have to detangle the parts, or you're going to have to pay your spring supplier to do some special packaging at its cost. If we were able to get into the design side as early as possible, we would be able to highlight those and basically overcome those types of challenges, as I call it, manufacturing and assembly challenges. We also want to define critical elements for the design. And critical elements for the design, there's kind of 4 of them. The working environment. We really want to understand where the spring is used. As I mentioned earlier, relief valves or valves. They work in gas applications and definitely liquid applications. And we want to understand what is flowing through there to help you get the right material and the right and what stress that material should be at in that application. We also want to define the dimensional constraints, and that comes back to, again, as we talk about spring industry tolerancing. We want to apply those tolerancing, those best practice tolerances to every application, because if you are defining tighter than that, you're always going to find disruptions. We want to know the required forces, and the required forces are very important, probably the most important and again, I'm going to highlight in a relief valve application. You want to make sure we were able to achieve that force at the lowest stress possible, so that valve operates well throughout its life, because it's a very critical application, right? Valve springs, safety relief valves are very critical. And service requirements. And then when I talk service requirements, I'm not going to be talking about dynamic application, static application. It kind of falls into the forces, right? We want to make sure that the forces are the lowest possible, so that valve basically could seat and operate over time and it doesn't leak or doesn't fail in service and create some hazardous situations. Here we're going to talk about design for manufacturability. So these are part of the critical design elements for springs, and there are 5 of them. The first one we're going to talk about in the next section is over tolerancing. So briefly, over tolerancing is a lot of times we see this on newly released drawings where when the spring manufacturer is late to the design process. Another design element is the spring index, which I'll get into again in another slide. Where is the ideal spring index for the spring? Also want to know the shape of the spring, what the material should be, and what the stresses are, and how to identify the stresses. So over tolerancing. What is over tolerancing? So I created just a simple, this is a valve spring design right here that we use. It's a commercial software we use, and I've inputted some inputs which are in the dark here. And what I thought this would be easier to show you visually. So what we talk about over tolerancing is a lot of times a customer will release a drawing to us, and they're going to say, I want the load at this, I want the load at this tolerance, I want the free length to be this, I want the total coils to be this, the OD to be this with this tolerance. And what that happens is you've kind of blocked and constrained the spring manufacturer, because when we are targeting, and I'm just going to cover 2 loads, right? When we're trying to achieve 2 loads, the rate is actually a calculated function of those 2 loads that you specify. And that free length has to float, because there are certain dimensions that you've already locked us in, and that free length must be adjusted to allow to center those loads. So you may, if you toleranced it, we may get the loads, but if you tolerance the free length, but the process won't be centered. So it's really important that when you look at putting up a design, that you focus on what's really, really critical to the design, and everything else kind of let that be for the spring supplier to be able to have the flexibility to make those adjustments. Spring index. So spring index is the mean diameter divided by the wire diameter. And the preferred range for a spring index, we say 4 to 12. Now, everyone out there is going to say that's a pretty small range. I've seen spring suppliers go much bigger than that, and the range can get larger. But you want to be in the most ideal area. 4 to 12, the spring ratio is giving you the best, tightest tolerance possible. Anytime you go, I mean, yes, you can make a spring out of a 30 index, which is probably the picture. If you can see my cursor, it's this spring here. This creates a lot of challenges for the spring manufacturer. They can make it, but you're going to have larger tolerancing on your diameter, your OD or ID. And there's also something that happens where the ends actually flip over. I don't know if anybody has seen that. We have some customers that we do a lot of valve springs with very big indexes, and we constantly struggle with the ends flipping over. It does throw the load off. Tight index here, this is a 3.5 index spring. That has its own design challenges and manufacturing challenges, because there's a tool that this spring gets coiled around that goes in the middle here. And that tool has to be small enough to fit in the ID. And as you know, it can break the tool. So it's going to add costs. I mean, it can be done, but the spring manufacturer has to probably add a higher cost to the part to allow for that possibility of that thing breaking. Different types of shapes of springs. So here I've pictured a cylindrical spring, which, let me get my pointer here. That's a cylindrical spring. Most common in the relief valve. I'm just going to talk about relief valve application. Conical spring, also pretty common, but not as common as cylindrical. Type of ends. There are 4 type of ends. Here is an open end spring that we're not going to see that in relief valve. No one, that does not, it's not practical. Closed end, which is here. You got your closed ends ground, and again a squared end, which is similar to a closed end. The most common in the spring, and the most common in the relief valve, again, are your conical ground and your cylindrical ground and closed ends. Cylindrical springs. So in this slide, I'm just going to discuss some performance and manufacturing benefits and drawbacks. Cylindrical springs, some of the performance benefits is the biggest one is the rate. The rate is linear. Below here, my pointer, here's a rate curve. Here's your 15 and 80%. And as you can see, this is a beautiful linear curve, something you would see on a cylindrical spring. Perpendicularity, which we talk about, is another word, squareness, how straight the spring stands to the vertical axis. Parallelism, how horizontal each end is to itself. Some of the drawbacks, performance drawbacks, solid height constraints. Cylindrical spring, as you know, you have a solid height, one coil stack on top of another coil. There's no benefit, and I'll talk about another shape that kind of gives you a benefit on a solid height. Manufacturing benefits, as we know, cylindrical springs are easier to manufacture, and they're easy to measure. As we all know, you could take a pair of calipers to it, measure the length, the OD. Drawbacks, and again, wouldn't see this in relief valves, but we do have customers on just other applications that want open-end springs, and sometimes they want them ground, and it's not practical. Open-end springs tangle really bad. Grinding them is even more difficult because you don't really have a square or flat surface to come into when you grind it. Conical springs. Again, we'll talk about some performance and manufacturing benefits and drawbacks. Some of the benefits: reduced weight. Conical spring, the shape of it, actually, if you stood the same cylindrical spring with the same base OD, that one would be heavier than this one. Increased deflection. And this comes back to, as I talked about, solid height constraint. This particular spring may not give you a coil into coil solid height. So when we say this, is you could manufacture this conical spring. So each coil goes inside itself, and you could basically compress it flat to one coil and give you a solid height of one wire size. So it gives you definitely increased available deflection. Performance drawbacks, and this is one of the big ones. It's not truly a linear rate. It is somewhat of a variable rate. 15 to 85% to test the rate really doesn't apply, even though literature shows it could. A lot of times when we are helping design a spring that's conical, it's very important to know the 2 points that the spring is being used at. And then at those 2 points, we help design and calculate the proper rate curve. You can't use the arbitrary 15 and 85% as on a cylindrical spring. Another thing is it's difficult to control concentricity. So when we talk about concentricity, it's not talking about squareness as on a cylindrical spring. It's actually talking about the top surface center to the bottom surface center of the coil and how concentric they are to each other. That's very, very difficult to give you a perfect concentricity. A lot of times it's even difficult to measure, requires special fixturing to do that. Grinding is very difficult. We do need special fixturing to grind the spring. You have to, it's in a conventional cylindrical spring, as it goes through the grinder, it falls out of the grinding fixture. On a conical spring, it doesn't. Someone has to actually remove it. So it does cost more money, conical spring, than a cylindrical spring would. End squareness. So end squareness, again, we're going to talk this cylindrical spring, but it's how square, perpendicular. When we talk squareness, we talk perpendicular and parallel the spring is. Commercial tolerancing is 3 degrees on a squared and ground spring. But when we talk about relief valves, we talk more 1 to 2 degrees. 3 degree may not be practical for relief valve application. And the reasons why is something that you probably are aware of: side loading, where the spring actually is pulling to one side, and that can create leaks, create some other wear on some seals. So when we offer design assistance, or a supplier may offer you design assistance, understanding the application is key, because if you're dealing with relief valves, we may be wanting to help you design to a much smaller squareness tolerance. Spring materials. Spring materials are, as you know, are very, very important to the design side of application. Some of the elements that we need to consider: corrosion resistance, probably very, very important. Conductivity, maybe not as much in the relief valve, but it is important to some other applications. Tensile strength is very important. Elastic limit, modulus, operating temperatures are very important. Of course, cost is very important to a customer. That we're helping design something at the most economical cost. And of course, availability. We don't want to help design a spring that is going to take a very long time to get, because the material is not available, the wire size is not available, it has to be all custom ordered. Some of the common materials. So some of the common materials are your high carbon steels, which probably the most common, as you've heard, probably a lot of people have heard, is the music wire. Your alloys, steel wire, your chrome silicon, chrome vanadium, was very popular maybe 20 years ago. I've seen a lot in the industry, people moving away from the alloy wires into more music and even into stainless steels, which is the next one here. Your really common ones is your 302s and probably your 17.7s for relief valve. Non-ferrous alloys, haven't seen many relief valves designed out of that, but you know they're really good for corrosion resistance and and connectivity. And we've seen a lot of high temperature alloys. Inconel X750 being one of the most popular ones, and that's for you can use it for two things, right? Very corrosive environments and then elevated temperatures. So here's just a material chart comparison and kind of what I said earlier. Your carbon steel here, which is your most common, offers a really high tensile, low corrosion resistance. A lot of times this material needs to have some post coating done to it. Operating temperatures are relatively low, not very, it's average conductivity, average cost, because it's an availability, a lot of different sizes are available. Alloy steels, similar, you know, high tensile, low corrosion resistance, need to have that post coating. They do better on operating temperature. Conductivity is same as music wire, but the cost is a little higher, and the reason why is it's certain sizes you need to buy a product of a coil. So unless you're going to have a large volumes, you may be paying a large upfront minimum cost for the material. Stainless steels, tensile's a little lower than your carbon steel, unless you're dealing with 17.7. This is more for your 302. High corrosion resistance, you know, great for those applications where you're dealing with certain gases. Again, unless the gases are not corrosive, they're for the price difference. We see a lot of valve springs on a 302 stainless steel. Operating temperatures are a little on the higher side, better than your carbon steel. Same type of conductivity, but of course, cost is a little bit more than your carbon steels because of the nickel content. And availability is good availability. Again, you can get a lot of different sizes. Non-ferrous alloys, again, not really seeing them in the relief valve applications. Low in tensile. They are high in corrosion resistance because of the copper content. They work medium to high on the operating temperature. They're very conductive, so they're great for any type of electrical type application. Costs are very high because of the copper content, and they're not that available anymore as they used to be. And then lastly, your exotic alloys. Those are your Inconel X750. I'll use an example. Tensiles are average. Corrosion resistance, really high. High in nickel, right? Very high in operating temperatures. I think X750 can get up to 500-600 degrees easily in an operating temperature. Not that conductive. Costs, again, very high. And availability, no one really puts this stuff on the shelf. It's got to be pretty much custom ordered. This next slide we're going to talk about stress levels and maximum percent of tensile strength. So stresses are very key to a spring design. A spring manufacturer always wants to make sure we're designing to the lowest stress possible for the customer. Here's an example of a compression spring made of music wire with ground ends. It's a typical valve application. And what I'd like to kind of highlight here is I'd like to just talk about what are stress levels and what is something you might see maximum tensile strength, or MTS, percent of MTS. So when we're talking about stresses, every single material, again using music as a case, there is a threshold that the material can get to. So for example, music wire, it's 45% of the maximum tensile strength. Below 45%, the spring is gonna function the most ideal. The stresses are going to be low. You're going to get great static life, great dynamic life. When you start designing into the zone that you're actually higher, you're at a 45 to 60. You're going to start seeing that the spring is going to take something called it's going to take a yield. It's going to take a set, and there's things we can do to remove that, which I'll talk later on. But what we're trying to make you understand is the ideal thing, again, we're just talking about carbon steels right now, is when you run your stresses that we try to maintain as low as possible. We know we can't always get there, but getting as low as possible will give you the best economical price, because we won't have to do any post processing. So overcoming high stress. So in that last slide, you saw the green line and then the red line. So there are things between that green and red line we can do to reduce the stress of the spring. And there's two things we do. We could do a set removal. A set removal is just a manufacturing process that we actually take the spring down to coil bind, and we may do that once, twice, or up to 3 times. And what that does is it actually cold works the material, and it removes that initial stress that's put into the wire. And that stabilizes the force over time. Another thing that we can do is we can shot peen the spring. Shot peening is just a manufacturing process where media impacts the spring at a controlled velocity. And that impacted zone basically creates a compressive residual stress instead of uncompressive. It has a great effect on fatigue life, but we really don't use that in the relief valve applications. It's more your cyclic applications, dynamic applications, like your engine valve springs and clutches. Here I'd like to just give you guys an example of a case story that we did for a customer. The application was a TXV metering valve, and we had it was a spring that was an old design that we've been doing for years. Customer came to us with an existing design, and we just started manufacturing it. And over time, the customer has been seeing that this product just wasn't performing as well as they'd like to. They were having issues with creep, a little bit of load loss, and there was a lot of tangling or nesting going on during the coating process. So we, over 10 years with the customer, we looked at redesigning the spring for them. And some of the things we did, it was a very simple change. We saw that we were doing a set removal on the spring. We're actually pressing that spring to solid height one time. And what we were finding is that we were reducing the stress for the customer, but not enough to where they can get 5 years out of the product. So we redesigned the spring, removing that, not having to do that set removal. We added dead coils to the end of the spring, and that did 2 things for us. It reduced the stress by lowering the gap, and it also prevented the nesting. So the customer here is having so many issues where they would get the springs like this, they'd be nested into each other. They had to use a wrench or a screwdriver to pry this apart, and you had a lot of coating missing. It just didn't go well. With this change, we were able to prevent any of that nesting from going on, and it saved the customer a lot of money in the long run, because we removed secondary operations for them. So, in summary, I'd just like to recap that highlighting getting the spring supplier involved early at the stage is ideal. It's ideal because the spring supplier will help you choose proper practices, manufacturing practices, to help identify any type of challenges in the assembly you're going to see in the future. So that goes to using spring industry tolerances, again, versus machine tolerances. So we're gonna tell you right up in front what those are and what tolerance that spring's going to see on the OD, ID, free length, and load. We're also going to help you prevent you from doing any over tolerancing, helping using a spring index, ideal spring index, choosing the right shape for your application, designing to the lowest stress as possible. Any way you can get us involved or your spring supplier involved early on in that stage is going to help you overcome any of those challenges that you might see later on the road that might reduce your chance for speed to market. So again, thank you very much for your time. I hope you've enjoyed my presentation, and I'll give it back to Julie.
Thanks, Chris. That was great and very informative. We do have a few questions for you, and we will try to get to as many of these as possible. Our first question is, what type of materials would be good in high temperature applications?
So I'll go back to that slide. So for so your exotic alloys, preferably Inconel X750, Inconel 718, work great in high temperature applications due to the amount of nickel content. They're again great for corrosive, but just as good in high temperature applications because of that.
Perfect. Our next question is, where can we find documentation on spring industry tolerances?
So there's two places you can find that. Definitely consult your spring manufacturer, spring supplier. They definitely have that and can share that with you. You could also go on the web. We've seen a lot of websites that have publications on that. The best one I would recommend is there's a SMI website, which is Spring Manufacturers Institute, and they have actual manuals you can buy that highlight all those tolerances.
Thanks, Chris. Our next question has two parts. Are we finding that lead times are going up? And are we seeing shortages of raw material?
So in answer, there is a short-term material delay that we are seeing in the industry. It is short-term. We don't see this going over a year, but yes, there is some delays of certain rods of material from our suppliers right now. But as we see this as more of a short-term issue, no more than maybe 3 to 6 months.
And are we finding any lead time delays with that?
Yes, you would see some as the material as there are material shortages. It's getting a little harder to get those materials into stock. So that would definitely increase the lead time to the customers. But as we say, we feel this is a kind of a short-term issue right now.
Great, thank you, Chris. That is all the questions we have for the presentation today. So I just want to remind everyone that this event was recorded, and we'll make sure you all have access to the recording in case you'd like to review any of the information Chris shared today. We'll send the link to that recording as well as contact information for our presenter, Chris Koska, in a follow-up email. Feel free to get in touch with Chris if you have any additional questions. So with that, I'd like to thank our speaker, Chris Koska, again, and everyone on the call for taking the time to attend this session. We really appreciate it and hope you have a great rest of your day.